Now, ferromagnetism. The individual atoms or ions or molecules in a ferromagnetic material possess a dipole moment as in a paramagnetic material. However, they interact with one another in such a way that they spontaneously align themselves in a common direction over a microscopic volume called domain. And each domain has a net magnetization. Typical domain size is 1 millimeter and the domain contains about 10 raised to 11 atoms. Means see here, see the figure, here some dipole moments are represented in the figure. Here each and every dipole here is not aligned in a particular one direction, but some dipole moments align in a particular direction. We can say these dipoles interact with each other, and in this small region, this particular number of dipoles are aligned in a particular direction. So if we take the vector summation of all these, then resultant magnetic moment of this domain, that will be as shown in this figure by this green arrow we can represent. Similarly, for nearby domain, suppose some dipole moments are aligned in this particular direction. If we take the vector summation of all these, then the resultant magnetic dipole moment of this entire region will be obtained as shown by this green arrow. So in this way, the domain structure is possessed by this ferromagnetic substance. And for each domain, the resultant magnetic dipole moments are randomly oriented. See, resultant of this one, resultant of this one, resultant of all other domains are randomly oriented. So net dipole moment again of the substance, that comes to 0. And therefore, in normal circumstances, this will not exhibit any magnetic characteristic. And see here, in a particular 1 millimeter size of the domain, 10 raised to 11 atoms are there, means 10 raised to 11 dipole moments are there. Clear up to this one? Thus, in a ferromagnetic material, the field lines are highly concentrated, and in non-uniform magnetic field, the sample tend to move towards the region of high field when the external field is removed. In some ferromagnetic materials, the magnetization persists. Such materials are called hard ferromagnetic materials or hard ferromagnets. Alnico, an alloy of iron, aluminium, nickel, cobalt, and copper, is one such material. Such materials form permanent magnets to be used among other things as a compass needle. On the other hand, there is a class of ferromagnetic materials in which the magnetization disappears on removal of external field. Soft iron is one such material. Such materials are called soft ferromagnetic materials. There are a number of elements which are ferromagnetic: iron, cobalt, nickel, etc. The relative magnetic permeability, that is greater than 1000. The ferromagnetic property depends on temperature. At high enough temperature, a ferromagnet becomes a paramagnet. This disappearance of magnetization with temperature is gradual. It is a phase transition, reminding us of the melting of the solid crystal. The temperature of transition from ferromagnetic to paramagnetism is called the Curie temperature, Tc. The susceptibility above the Curie temperature it implies in the paramagnetic phase is described by chi, that is equal to C upon T minus Tc, where T that is greater than Tc.